For the first time, a science experiment has measured Earth's ability to absorb neutrinos, the smaller-than-an-atom particles that zoom throughout space and through us by the trillions every second at nearly the speed of light. The experiment was achieved with the Icecube detector, an array of 5,160 basketball-sized sensors frozen deep within a cubic kilometer of very clear ice near the South Pole. The results of this experiment by the Icecube collaboration, which includes Penn State physicists, were published in the online edition of the journal Nature on November 22. This achievement is important because it shows, for the first time, that very high-energy neutrinos can be absorbed by something, in this case, the Earth, said Doug Cowan, professor of physics and astronomy and astrophysics at Penn State. The first detections of extremely high-energy neutrinos were made by Icecube in 2013, but a mystery remained about whether any kind of matter could truly stop a neutrino's journey through space. We knew that lower-energy neutrinos pass through just about anything, Cowan said, but although we had expected higher-energy neutrinos to be different, no previous experiments had been able to demonstrate convincingly that higher-energy neutrinos could be stopped by anything. The results in the Nature paper are based on 1 year of data from about 10,800 neutrino-related interactions. Cowan and Tyler Anderson, assistant research professor of physics at Penn State, are members of the Icecube collaboration and co-authors of the paper. The pair helped to build the Icecube detector and are contributing to its maintenance and management. This new discovery with Icecube is an exciting addition to our deepening understanding of how the universe works. It also is a little bit of a disappointment for those who hope for an experiment that will reveal something that cannot be explained by the current standard model of particle physics, said Cowan. The results of this Icecube study are fully consistent with the standard model of particle physics, the reigning theory that for the past half-century has described all the physical forces in the universe except gravity. An archived news story includes a video showing the construction of the Icecube detector. Neutrinos first were formed at the beginning of the universe, and they continue to be produced by stars throughout space and by nuclear reactors on Earth. Understanding how neutrinos interact is key to the operation of Icecube, explained Francis Housen, principal investigator for the Icecube Neutrino Observatory and professor of physics at the University of Wisconsin-Madison. We were of course hoping for some new physics to appear, but we unfortunately find that the standard model, as usual, withstands the test, Housen said. Icecube's sensors do not directly observe neutrinos, but instead measure flashes of blue light, known as Cherenkov radiation, emitted after a series of interactions involving fast-moving charged particles that are created when neutrinos interact with the ice. By measuring the light patterns for these interactions in and near the detector array, Icecube can estimate the neutrinos' energies and directions of travel. The scientists found that the neutrinos that had to travel the farthest through Earth were less likely to reach the detector. Most of the neutrinos selected for this study were more than 1 million times more energetic than the neutrinos produced by more familiar sources, like the sun and nuclear power plants. The analysis also included a small number of astrophysical neutrinos, which are produced outside the Earth's atmosphere, from cosmic accelerators unidentified to date, perhaps associated with supermassive black holes. Neutrinos have quite a well-earned reputation of surprising us with their behavior, says Darren Grant, spokesperson for the Icecube collaboration, a professor of physics at the University of Alberta in Canada, and a former postdoctoral scholar at Penn State. It is incredibly exciting to see this first measurement and the potential it holds for future precision tests. In addition to providing the first measurement of the Earth's absorption of neutrinos, the analysis shows that Icecube's scientific reach extends beyond its core focus on particle physics discoveries and the emerging field of neutrino astronomy into the fields of planetary science and nuclear physics. This analysis also is of interest to geophysicists who would like to use neutrinos to image the Earth's interior in order to explore the boundary between the Earth's inner solid core and its liquid outer core. Icecube was built to both explore the frontiers of physics and, in doing so, possibly challenge existing perceptions of the nature of the universe. This new finding and others yet to come are in the spirit of scientific discovery, said James Whitmore, Program Director in the National Science Foundation's Physics Division. Physicists now hope to repeat the study using an expanded, multi-year analysis of data from the full 86-string Icecube array, and to look at higher ranges of neutrino energies for any hints of new physics beyond the standard model.